Let's define the types of discontinuities for a given value of a function. So the first two types here are removable discontinuities, with the one on the right being a point discontinuity. So for a general removable discontinuity, we can remove it by defining this point. And similarly for a point discontinuity, we can remove it by shifting this value of x to fill that discontinuity. So for the removable discontinuity, f of k is undefined. But the limit as x approaches k from both sides is equal, and therefore the limit exists. Now for the point discontinuity, we can see that f of k is defined, and the limit as x approaches k from both sides is the same, so that also exists. But for a point discontinuity, this limit is not equal to f of k. Now this discontinuity is a jump discontinuity, so in this case f of k exists, but the limit as x approaches k from both sides is different, so therefore the limit does not exist. And the final type of discontinuity we'll look at is an essential discontinuity, or an asymptote. So in this case, the function is not defined at k. And in this case, because the function approaches two different values from both sides, then the limit as x approaches k does not exist. Let's identify the types of discontinuities. So at x equals minus 3, the function is not defined. And the function is also unbounded, such that the limit is minus infinity. So therefore we have an essential discontinuity, or an asymptote. Now at x equals 1, the function is defined and evaluates to 1.5, and the limit's also defined. But as we can see, the limit's not equal to the value of the function. So therefore, we have a point discontinuity. Now at x equals 2, the function is not defined, and the limit does not exist. So this is another example of an essential discontinuity, but the function approaches two different values from both sides. And at x equals 3.2, the function exists, but the limit does not exist. And therefore we have a jump discontinuity. Let's determine the types of discontinuities in the function and the x values at which they occur. So first we should try to factorize where possible. So because we have a quadratic, we can try to factorize the numerator. Now we may recognize that we can cancel out the x minus 1, so therefore at x equals 1, we have a removable discontinuity. And at x equals minus 4, the function's unbounded, so we have an essential discontinuity, or an asymptote. Let's define three conditions to determine if a function is continuous at a particular point x equals k. So the first condition is that the function must be defined at x equals k. So using this example, at x equals 3, we can see that the function is defined. And the limit of f of x as x approaches k must also exist. So as x approaches 3 from both sides, then we can see that the function is approaching the same value. And the third condition is that the limit as x approaches k must be equal to f of k. And we can see that this is also satisfied in this example. Let's determine if f of x is continuous at x equals 3. So the first condition is that f of 3 must exist, and that is the case, and the function is equal to 11. And the limit of the function as x approaches 3 must also exist. So we check the limit from the left first. So as x approaches 3 from the left, the function approaches 11. And similarly, as x approaches 3 from the right, the function also approaches 11, and therefore the limit as x approaches 3 exists. And the third condition is to check if f of 3 is equal to this limit. And we can see that this is the case, and therefore the function is continuous. Let's determine if this function is continuous at x equals 3. Well, first we check if f of 3 is defined. And as we can see, the function is not defined at x equals 3. So therefore, the function is not continuous at x equals 3. And now just for completeness, if you check the limit as x approaches 3 from the left, so that's equal to 11. And if you check the limit as x approaches 3 from the right, which is also equal to 11, so the limit exists, and therefore we have a removable discontinuity. Let's determine if this function is continuous at x equals 1. Well, first we need to check that f of 1 exists. So as we can see, f of 1 is equal to 3. And now we check if the limit exists as x approaches 1. So from the left hand side, the limit evaluates to 3. And as x approaches 1 from the right hand side, the limit is 9. So therefore the left hand limit is not equal to the right hand limit, and therefore the limit of the function as x approaches 1 does not exist. So therefore the function is not continuous at x equals 1. A function is continuous on an open interval ab if it's continuous at each point in the interval. So as we can see, if we don't include the endpoints, we can draw the function without lifting the pen. Now a function is continuous on a closed interval if it's continuous at every point in the open interval, and the right hand limit at a is equal to the value of the function at a, and the left hand limit at b is equal to the value of the function at b. So for this function here, as x approaches a from the right hand side, it's not equal to f of a. So therefore the function is not continuous at this end of the interval. Because if we were to draw this function, we draw it up to a, and then lift the pen and continue drawing it. Now as x approaches b from the left hand side, the limit is equal to the value of the function at b. So therefore we don't have to lift the pen to continue drawing the function at b, and therefore the function is continuous at b. Let's determine if this function is continuous. So given it's a piecewise function, we can see that the cubic, the constant, and the linear component are all continuous. So all we need to do is check the endpoints for continuity. So for x equals 2, we can see that f of 2 is defined. And as x approaches 2 from the left, the function approaches 5. And as x approaches 2 from the right, the function also approaches 5. So therefore the limit is defined at x equals 2. And we can see that the value of the function is equal to the limit, so the function is continuous at x equals 2. And doing the same check for x equals 3, the function is defined at x equals 3. And as x approaches 3 from the left hand side, the function approaches 5. And as x approaches 3 from the right hand side, the function approaches 5. So the limit is defined at x equals 3. And the value of the function at 3 is equal to the limit at 3. So therefore the function is continuous at 3. And is thereby continuous over the interval from -infinity to infinity. A discontinuity at a particular value of x is removable if the limit of the function as x approaches k exists, and if the function is not defined at k, or the value of the function at k is not equal to the limit. So here is an example of a removable discontinuity where f of k is undefined. And in contrast, if the function was defined at k, you'd have a type of removable discontinuity called a point discontinuity. But let's look at this general case. So the domain of this function can be written as follows. So the function is defined for all values of x apart from x equals k. So if we look at a boundary to the partition of the function's domain, so that will be at x equals k, well, the expressions defining the function on both sides of the boundary must be equal to each other, and they must be also equal to the value of the function at the boundary for this function to be continuous at the boundary. So effectively we insert a value for the function to make it continuous and thereby removing the removable discontinuity. Identify the type of discontinuity in the following function and remove it. So we can see that the individual expressions for the function are all continuous, so we need to check if it's continuous at x equals 3. So the value of the function at 3 is 5. And now we check the limit as x approaches 3 from both sides. So from the left hand side, the function approaches 11, and from the right hand side of 3, the function approaches 11. So therefore the limit is equal to 11, and it exists. So now we can see that the value of the function at 3 is not equal to that of the limit, and because the function is defined, we have a point discontinuity. So to remove this discontinuity, we need to set the value of the function at x equals 3 to be the same as that as the limit. We can extend limits to include infinite limits. And we can explain asymptotic and unbounded behavior of functions using limits. So here's an example of a function that has an asymptote. And to find the vertical asymptote, we take the limit as x approaches a value in the denominator. So as x approaches 2 from the left hand side, the function approaches -infinity. And as x approaches 2 from the right hand side, the function approaches +infinity. So because the function approaches 2 different values from both sides, the limit does not exist in this case. And the function is also undefined at x equals 2, so there's a vertical asymptote, which is an essential discontinuity. We can also extend limits to include limits at infinity, and these describe the end behavior of a function. So effectively they give us the horizontal asymptotes. So if we consider this function and take the limit as x approaches infinity, well, we can see the fastest growing term in both the numerator and denominator. So this function nearby approaches 2. So this limit tells us that we have a horizontal asymptote at f of x equals 2. And similarly, if you take the limit as x approaches minus infinity, well, we have x in both the numerator and denominator, so we're still going to get a positive result. So the limit evaluates to 2 also. And that gives us the same horizontal asymptote. We can also use infinite limits to compare the relative magnitudes of functions and their rate of change. So if we look at these different types of functions, from trigonometric to exponential, well, we can see that as x approaches infinity, the trigonometric function oscillates, while the logarithmic function grows slower than the linear function, which grows slower than the parabolic function, and that grows slower than the exponential function. So this order of growth is not so obvious if we take smaller values of x, as we can see. So to determine the relative magnitude of a function f of x with respect to g of x, we take the limit of their quotient as x approaches infinity. And if you have asymptotic behavior, then this can be written using the quotient rule as follows. So if these functions approach horizontal asymptotes, and they don't grow indefinitely as we can see here, we can obtain a finite relative magnitude of the function f of x with respect to g of x.